No? No? We shouldn't do that? Okay. You got stuff to do. There's nothing to do but algebra. All right, so let me redeem this. So here is the corrected formula. So sorry about that. Example 1, x cubed minus 8 is x cubed minus 2 cubed, which we're thinking of as a equals to x and b equals to 2. So that is x minus 2 times x squared plus 2x plus 4. All right.
There we go.
Because 2 cubed is 8. Yes, but the pattern is a minus. But you're fine. Okay, so again, are we done factoring?
No.
No, we need to understand, can this be reduced or not? If we complete the square here, x plus 1 squared minus 1 plus 4 is x plus 1 squared plus 3. Ah. Right? Hey, wait a minute.
Oh, we forgot to put a 1.
I need to, for the sake of the next section. You gotta know your weaknesses. All right. I've done nothing but math my whole adult life, but I still just remember this stupid thing wrong. Yeah.
So you also have to put a square over the next -1.
Oh, I don't though, because that's the method of completing the square. We take half of the x coefficient, we add it to x, we square that,
So
we subtract 1. That's not inside the square. That's not. Yeah.
But I thought that was it. But the one I'm talking about is in a different section.
Well, you'll have to tell me later, Michael. All right, so listen, we're done with this one. This is completely factored over the reals. Why? Because we have x minus 2 and we have this quadratic, but the quadratic, as you can see from what's in blue, is prime, right? So this shows this is a prime polynomial. It cannot be factored over the reals. So there
Since 3 is a prime number.
It's because it's the sum of squares here.
So,
But you are right though. 3 is a prime. You are right about that.
How do you know that this equation is a prime? I guess
Because it's a sum of squares.
Oh, a sum.
Whenever we complete the square, if after we complete the square we get plus a number, that means it's a prime polynomial. Because a prime quadratic, it can't be factored. If instead of getting a plus 3 there, we ended up with a minus 3, we could have factored it. All right? Okay, so moving on here. What if we were up against example 2? Suppose we had, let's say, 2x plus 1 cubed. Oh, no. That one's my bad, guys. Let's not do that. I have a penchant for making examples which are too horrible if I'm not careful. So let's not do that. Excuse me.
It's okay.
Thank you. 10x cubed plus 8. Well, not 8. Plus 17. So this requires a little bit more imagination. So we're seeing it, it's like a cube plus something, so it's kind of the sum of cubes pattern, but it doesn't look like a cube yet, does it?
Nope.
So we want to think about 10x cubed equals to a cubed. We want to think about 17 as being our b cubed. So what would that make us think of A as being?
Equals A. So, hold on.
So if we take the cube root of this, right? This tells us that A is equal to like x times the cube root of 10. If I take the cube root of this, I can see B is equal to the cube root of 17. Do you guys know what the cube root of 17 is? Yeah, me neither. So
Oh, wait, don't.
I'm not erasing. Michael, I'm just erasing the.
I just want to get every information possible.
Keep in mind that if you do not get something, there's a couple things we can do. Number one, we can watch the video, right? Because I'm recording this. Oops. I will be recording this soon. And so you can look at the tape and see what I wrote there. But the other thing you can do is just take a picture with your phone if you get behind. Sorry for the ears of the people at home. May have just smashed them on the floor. Oops. Anyway, so all right, so here we go. We've got A plus B is going to be x times the cube root of 10. B was the cube root of 17. And then what's A squared? Well, A squared is x squared times the cube root of 10 squared minus x times the cube root of 10 times b, which is the cube root of 17, plus the cube root of 17 squared. So what I'm doing is I'm plugging in what a and b are into the values. So let me tell you guys a fun fact. Anytime we have one of these difference of cubes or sum of cubes problems, there's a simple reason that completing the square always works out to a prime. Right? So like the thing that happened in the first example always happens. So if you guys want, you can just claim, and I wouldn't be offended, that this is prime. It has to be, actually. Right? Now, I could tell you the reason. The reason's pretty simple. It's that the graph, if we were to look at the graph of this polynomial, it's a cubic graph, and it only goes through the x-intercept once. So it can't have more than one real zero, which means that it must be that the other thing has complex roots, which means it's one of those prime ones. That always happens. So I'm just allowing you to use that as like a theorem. You can just use it, right? But, yep.
Why is x squared in the left?
Well, you could write it the other way if you wanted. I mean, x squared times the cube root of 10 squared is equal to the cube root of 10 squared times x squared. That's true.
Oh, so they're the same thing.
Other questions? No. Yeah.
Can you explain why we're allowed to claim it as a prime because it only touches the x or the x-axis once?
Oh, okay. Well,
Like geometrically.
yes, but this is a bit of time travel. So, in the sense that this is something. So the graph of this looks something like this. And so like a cubic graph looks like that, and because we have something called the factor theorem, And the factor theorem says that you only have a 0 if you have a factor. Every 0 of the graph comes with a factor of the polynomial. This graph only has 1 0. Therefore, we cannot factor this piece into real factors. Like it has to,
That makes sense.
yeah, that's it. And that always happens. Whether you've got your, so the picture for this one, it you know, again, I don't test on graphing of cubics yet, guys, because like the graphing cubic stuff is a little bit later. Well, let me not. Let me not say more until I have something in front of me to look at. Anyway, what I should say is I have not formally covered graphs of cubics yet in this course, right? We will. So again, it only goes through that one point, which is why there was just this x minus 2, and there wasn't anything else to find. But anyway, I'm responding to his question. Otherwise, I wouldn't write these on the board, right? So, all right. So let's go on here.
Oh, so the x right here is the x-intercept of the graph.
That is true. The x-intercept of this graph would be where this is equal to 0, which is like what? If we put this equal to 0.
X.
It's kind of ugly, but that is where it goes through 0. All right, so. Goodness. Excuse me. Setting it equal to 0.
I see.
All right, so there is a class of problems where the difference or the sum of cubes formula is super useful. There's another thing I should tell you about. And that other thing is the binomial theorem. Do you guys know about the binomial theorem?
Oh.
Binomial theorem.
Oh. Let me catch up.
So this is a way we can multiply a binomial, a sum of two terms, to any power we like in a very easy way. So here, I'll show you guys. If we have, let's say, a plus b squared, what's that look like? Huh. Well, oh, there it is. Whew, looking for a fresh one. So a plus b squared. Oh, it's not fresh. This is a squared plus 2ab plus b squared. All right. Now, I guess even before that, what's a plus b equal to?
A plus b.
I mean, what's a plus b? This is kind of stupid, but what's a plus b to the 1 equal to? Well, it's a plus b, right? Now, what's a plus b, good grief, cubed, equal to? That's a cubed plus 3a squared b plus 3ab squared plus b cubed. Do you know what a plus b to the 4th is? It's a to the 4th plus 4 a cubed b plus 6 a squared b squared plus 4ab cubed plus b to the fourth. Now you might wonder how I know these. Let me tell you my secret. So first of all, there's a really simple pattern to what I'm doing. See the formulas? Look at the formulas. As you go left to right, the power of a goes from the highest power and it drops down to nothing, right? And the other way, the b raises to the highest power, but it starts at nothing. Do you see that? Notice the pattern. Every term, the power of b raises by 1, and every term the power of a drops by 1. The net sum of the powers, it's always whatever we're looking at. Like if it's the fourth power, then we have a net number of 4. Like for example, this a squared b squared has a net of 4. Yes?
How did you get 6?
That's the secret. So there's this fellow called Pascal, and he made this thing called a triangle. So this is Pascal's triangle. I start with a 1 up on the top, then I keep putting 1s on the end, all right? And then the rule is you take the whatever's above and you add. 1 plus 1, 2. All right? And then I put a 1 on the end. I add the numbers above. 1 plus 2, 3. 1 plus 2, 2 plus 1, 3. All right? And then you're wondering where that 6 came from. We're getting there. And then 1 on the ends. 1 plus 3, 4. 3 plus 3, 6. 3 plus 1, 4. That's where the 6 comes from. Notice that the pattern is, there's this 1 here. That's this 1. This 4 is this 4. This 6 is this 6. This 4 is this 4. And this the 1 here, right, is, I'll put a back man there. That's the pattern. So this is the binomial theorem, which says that if you want to calculate like a plus b to a power, you can write down Pascal's triangle and just like read off the coefficients for whatever you're expanding. Just like that.
1a to the 4.
So, example 3, if I have x cubed plus 3x squared plus 3x plus 1, and I'm asked to factor that, what should I do? Now, I will admit, to me, this is a challenging factoring question if I come across it in the wild. Unless what? Unless I have on my mind this right here. Unless I can recognize those as binomial coefficients and go, oh, that's just what? That's x plus 1 cubed.
Plus 1, 3.
To the third power, right? That's just that. So to my knowledge, there's really only about 3 reasonable ways to give you guys like a cubic and ask you to factor it. To make a cubic a reasonable factoring question, either it's like the sum of cubes or the difference of cubes. That's straightforward. We use the sum of cubes or difference of cubes formula, right? The other way to make it reasonable is exceedingly silly. If there's like if there's an x on everything, you can like factor out an x. That makes it easy, right? But this is the other thing that can happen, is you might be able to use the binomial formula. Now, let me do another one here. What if we're up against like 8x cubed? Let me behave here. You got to know your limits. 8x cubed plus, let us say, 9x squared plus 81 x plus 27. Now, let me just help you guys to see the pattern. What we're looking at is x cubed plus 3 times 3x. Oh man, yeah, 3 times 3x. Just a second. 3 times 3x squared plus 3 times... One second, guys. I may have done it wrong. Just hold on for a second here. Yeah, I messed up my example. So I shouldn't have put an 81 here. What should I put? I meant to put a... What do I mean to put there? 18? Heart's in the right place? Add another 9? Yeah, 27. So if I put a 27 there, it's a friendly problem. If I put the 81 there, it's a very, very unfriendly problem. So let's make it friendly. Do you guys remember friendlies? You're too young. Never mind. Anyway. Oh yeah, there used to be like a restaurant. Yep. So then we have what? Now we've got the right pattern for the binomial theorem. This is what? X plus 3 cubed. So the binomial theorem is it has many applications actually to counting. So I don't know if do you guys have any classes with counting problems in them? Like, suppose you have a deck of cards. You got 52 cards, right? And you want to pick 4 cards, right? Like, how many different possible decks are there to pick?
5.
So that's 1 out of 5. So that is 52. Choose 4 is what the symbol people use for that. You guys don't have to know this. This is for your, 52 choose 4. So like that is what these numbers mean. Like this right here, 6 is actually 4 choose 0. 4 choose 2. If I have 4 objects and I'm choosing 2 from it, there's 6 distinct ways I can choose. Right? If you have like A, B, C, D is your objects, think about that. You can either do A with B, you can do A with C, you can do A with D, you could pick A, you could pick B and C, you could pick B and D, or you could pick C and D. You do not need to write this down. Relax. It's not part of this will not be tested.
Okay.
This is called 4 choose 2.
What's that triangle called again?
That's Pascal's triangle. So the meaning of the numbers you also can think about in terms of probability. And I'm pretty sure that there's some discussion of that in the appendix in the text if you want to read more about it. So this stuff is in the appendix. But all right, so I'll let you guys get ready. I'm going to go grab your quiz and then we'll get to it. Okay, guys?
All right.
All right. What's that? I will top hat when I get back, yes. And no, I have not taken attendance yet, so I appreciate that. Thank you, thank you.